Welcome, everyone. Today, we are diving into an absolutely critical part of computer science, the world of software testing and debugging. We're going to break down exactly how you can find and completely destroy the bugs hiding out in your code. I want you to think of this explainer like we're prepping for the ultimate space mission, because in the real world of computer science, there is absolutely zero margin for error. Seriously, every single calculation and logic check has to be 100% perfect before launch. So let's dive right in. Now, before we write off testing as just some boring chore we have to do at the end of a project, I want you to consider the infamous Ariane 5 disaster from 1996. We're talking about a situation where a single piece of untested code literally blew up billions, yes, billions with a B, of dollars. This wasn't just a minor, annoying glitch. It was a catastrophic failure. Why? Because the software tried to stuff a massive 64-bit floating point number into a tiny 16-bit space. It's like trying to park a massive semi-truck in a compact car spot at full speed. The rocket completely deviated from its flight path, broke apart, and self-destructed a mere 37 seconds after launch. So we are talking about incredibly high-stakes environments here. Understanding the precise differences between testing methods isn't just some academic exercise to pass a test. It's about making sure massive, complex systems don't fail in the real world. All right, so here is our roadmap for today. We're going to arm you with all the tools you need to defeat these bugs. We'll start by looking at the high stakes of testing. Then, we'll identify the 3 specific types of errors you'll face. After that, we'll look at how to use automated IDE debugging tools, followed by how to manually debug using trace tables. And finally, we'll wrap up with formal beta testing and test data. Let's get to it. Okay, Section 1, the high stakes of software testing. Let's actually look at when this critical testing happens in the overall development cycle. Testing is generally split into 2 distinct phases, alpha testing and beta testing. Alpha testing is done in-house by the developers during the actual programming phase. You can think of it like tasting the soup while you're still cooking it in the kitchen. It's meant for catching those foundational bugs in a safe, controlled environment. Beta testing, on the other hand, is the formal testing done by the actual end users once the software is fully built. This is opening night at the restaurant. It tests the system under real-world stress. Both of these phases are absolutely required, one after the other, to ensure a piece of commercial software is actually viable. Moving on to Section 2, the 3 types of errors. It's time to identify our main antagonists in this debugging process. Every single bug you're ever going to encounter will fall into one of these 3 tiers, and they escalate in danger, from simple typos all the way to silent, deadly logic failures. First, we have syntax errors, which are basically just spelling mistakes. Then, runtime errors, which are those unexpected crashes that happen when the program is actually moving. And finally, logical errors. Honestly, these are the absolute worst. They are the silent killers. The program runs beautifully, the system gives you a green light, but the rocket still blows up because you told it to turn left instead of right. When you're analyzing a program, you must be able to explicitly distinguish between these 3. So first up is the syntax error. This is basically just bad grammar in your code. Maybe you missed a colon or you misspelled a variable name. Think of it like writing an English essay but forgetting every single capital letter and full stop. The reader, which in this case is the computer, simply cannot understand what you are trying to say. In programming, if you spell the command print as PRNT, the compiler just throws its hands up in the air and refuses to build the software. It is an immediate, hard stop. But hey, the good news, these are by far the easiest errors to fix. Modern IDEs are incredibly good at catching these syntax errors immediately. It's literally like having a built-in spell checker for your code. As we can see here, the IDE isn't just telling you there's an error somewhere, it's highlighting the exact line with a squiggly red underline. And it even offers a drop-down menu of potential fixes. This gives you instant diagnostics, meaning you can spot and correct these typos before you even try to compile the program. It's a lifesaver. Next up is the runtime error. Now this is a much trickier villain. It hides in the shadows until you actually hit run and then bam, it causes the program to crash completely. This happens when the code is grammatically correct, the spelling is totally fine, but you've asked the computer to do something that is physically impossible. Maybe you asked it to divide a number by 0, or you've caused an overflow error, which is like trying to pour a gallon of water into a tiny teacup. Or, and this is super common, you've tried to force text into a space that is strictly reserved for numbers. The program compiles just fine, but the exact moment it hits that impossible instruction during execution, it dies. Let's look at a perfect real-world example of this. Here, the programmer tried to put a text string into an integer variable. The program naturally panicked and just halted. Look at the code snippet. The programmer declared input 2 as an integer. We all know that means it can only hold whole numbers, right? But then on the very next line, they try to assign the word hello to it. So the computer tries to run this, it hits that line, realizes it can't put letters into a number box, and throws an invalid cast exception. This is a classic runtime error caused directly by a data type mismatch. And finally, we arrive at the most dangerous threat of all, the logical error. This one is terrifying because it produces 0 error messages. None. The computer is doing exactly what you told it to do. You just gave it the wrong formula. The IDE thinks everything is absolutely fantastic. There are no red squiggly lines. There are no runtime crashes. The program executes from start to finish perfectly. But instead of calculating the area of a circle, you accidentally calculated the perimeter. Just because your code runs perfectly doesn't mean it's right. You have to manually verify the logic. So, how do we fight back? Let's move to Section 3, Automated IDE Debugging Tools. To tackle syntax and runtime errors, we need to use our automated weapons. One incredibly powerful tool built right into your IDE is the breakpoint. This essentially lets you pause time and step through your code, line by line. Imagine you're watching security camera footage of a bank robbery, and you need to pinpoint the exact millisecond the thief entered the vault. You wouldn't just watch the tape at double speed, right? You'd pause it right before the critical moment and step forward frame by frame. That is exactly what a breakpoint does. You click the margin of your code editor, a little red dock appears, and when the program reaches that specific line, it freezes execution. This allows you to observe the changing state of all your variables at that precise step. A breakpoint lets you hover over your variables mid-execution, which is how you catch exactly where a calculation goes completely off the rails. Check this out. The execution is paused right at line 14. Down below, in the locals window, we can see the current status. Length is 8, height is 2.5, but area is showing up as 10.5. No, wait a minute. 8 times 2.5 is 20, not 10.5. Boom! The programmer immediately spots the logical error. They accidentally use an addition sign instead of a multiplication sign. Without that breakpoint, freezing the execution and showing those variables in real time, catching that error would have been like finding a needle in a haystack. Okay, Section 4, Manual Debugging Using Trace Tables. Because automated tools can't catch every logical error, we have to pull out our ultimate manual weapon. We hunt down these tricky logical errors through a process called dry running. This is where you literally become the computer and you step through the algorithm completely manually. To dry run code, you just follow these 4 steps. Step 1, set up your table, making sure every single variable gets its very own column. Step 2, you act as the CPU. You read line 1 and you do what it says. You read line 2 and do what it says. Step 3, every single time a variable changes its value, you record that new value on a new row in your table. And finally, Step 4, you compare your final manual output against what the result actually should be. Let's look at how this trace table systematically records the changing values of x, y, and count during a loop. Look at our columns, x, y, count, and output. The initial values, 20, 6, and 0, go right on the first row. Then the loop kicks off. X is reduced by 6, so 20 becomes 14. Count is incremented to 1. Then we repeat. 14 becomes 8, count becomes 2. 8 becomes 2, count becomes 3. At this point, the loop condition checks if x is greater than y. Well, 2 is not greater than 6, so the loop exits. The final output is 3. This table is a thing of beauty. It's clean, it tracks every single iteration perfectly, and it leaves absolutely nowhere for a logical error to hide. Which brings us to Section 5, Beta Testing and Test Data. Once you've cleared out the bugs, you have to face the final boss. You have to stress the system with formal beta testing. To make sure your software won't just break the second it hits the real world, your test schedule has to cover 4 very distinct categories of data. First is normal data. This is just what the system expects to process on a good day. If a test is scored out of 100 and input of 45 is valid, normal data. Then there is abnormal data. This is unexpected stuff the system should completely reject, like someone typing the letters TNEN into a number field. Then we have extreme data, which represents the absolute outer limits of acceptable values, like a 0 or 100. And finally, boundary data. This is data that sits right on the knife's edge of an accepted or rejected decision point. Now, it is incredibly common to confuse extreme and boundary data, so let's clear that up right now. Remember, extreme is the absolute limit of the scale, while boundary straddles the edge of a specific condition. Listen to me closely here, because this is crucial. Extreme data tests the boundaries of the entire system. If a test is out of 100, 0 and 100 are your extreme data points. They are totally valid, but they are at the absolute edges. Boundary data, however, is all about the internal logic, the if statements inside your code. If a student needs exactly 80 marks to get an A grade, that 80 is your boundary. So you test 80 to make sure it gives the A, and you test 79 to make absolutely certain the program rejects it and hands out a B. Boundary tests the exact split second where the logic flips. Definitely memorize that distinction. So as we wrap up, I want to leave you with a thought to ponder. If an automated IDE is so smart that it can catch missing punctuation and prevent divide by zero crashes, why are logical errors still considered the absolute most dangerous threat to a mission-critical system? Well, if the computer literally can't flag a logical error, who is ultimately responsible for catching it before the rocket launches? The answer, of course, is you. You are the ultimate debugger. Understanding these testing phases, hunting down those 3 types of errors, utilizing your IDE tools alongside manual trace tables, and carefully categorizing your test data, these are your vital tools for mission success. Thanks for joining me on this deep dive. Until next time, keep testing and keep building great code.